All right, here we go. Last lesson of the year before review. And it's a good place to finish because it's going to bring us full circle and sort of kick us off with a review of limits. So we're going to be learning about this thing called L'Hopital's rule, another French guy, L'Hopital's rule, and how it can help you find some limits of things that when we first encountered them, because we didn't know what a derivative was, we could not. Today we're just going to focus on the how, and then next class we'll focus on why this works. So first, just a refresher on limits. What a limit is it's a question, right? What value is f of x approaching as x gets arbitrarily close to some value a? Even if we never get there, right? Like if you have a removable discontinuity, you could still have a limit, right? The limit would exist in this case because the left hand and the right hand limits are the same. So don't forget that. Those are the key points to remember, refreshing that a limit exists basically if f of x is approaching the same number from the left and the right as x approaches some a, even if we never get there. And so if we're given some function, like we're actually given, f of x equals and some function, our current flowchart for finding limits, the one that people forget, oddly enough, people just kind of stare at this, always try to plug in a number. Just always start out by plugging in a, right? So if you're approaching some value a, literally just plug it in. If you get that value of a, like say I ask you just for a normal parabola to plug in this value, yeah, that's the limit. The limit is the value of the function, and that would make it continuous. But where we came up with problems was where we had things in indeterminate forms. Indeterminate forms such as division by zero. But you remember that wasn't the end of the story because like I said above, you could have a hole. You could have a removable discontinuity, and you would need to investigate further because the limit might not exist or might actually exist even if it doesn't get it from plugging in originally. And if we exhausted our factoring and we said, okay, it's not factorable, then usually the limit did not exist, but not always. And so let's consider two motivating examples. First, on the left, and I've kind of already graphed this. And so let's say, again, you want to have the mindset today, these graphs are here to help us explain, but pretend you did not have this graph, if this was on the non-calculator section of the exam. If it was on the non-calculator section of the exam, the first thing I would expect you to do is to take this and plug in 2. 2 minus 2 over 2 squared minus 4. Well, you'd get 0 over 0. And I'm going to really start to head this off. Never actually write 0 over 0. If you write it, cross it off because it's not actually going to be true, as we're going to see. But what we learned was when you get that 0 over 0, something that you can do sometimes is you can factor. And so this is the same thing as the limit as x approaches 2 of x minus 2 over x plus 2 times x minus 2. So we'd factor that out, x plus 2 times x minus 2. The x minus 2's would cancel. And what we'd be left with, well, x minus 2 divided by x minus 2, this is the limit as x approaches 2 of 1 over x plus 2. And that we can just find is 1 over 4. And as you can see on the graph, this is that exact example. We have a removable discontinuity, and the limit does exist. And so bringing us way back, start by trying to plug in, and if plugging in doesn't work, if it gives you a division by 0 of some kind, try factoring. But that's not always going to work. And so, for example, say you had the cosine of x minus 1 over x squared minus x. Well, this right here, cosine of 1 minus 1, the cosine of 1, quick unit circle, cosine of 1 is right here. So that's 1 minus 1, that's 0. If we plug in 0 here, 0 squared minus 0 is obviously 0. So we have this sort of 0 over 0 deal again. And if we look at the graph, we can tell, right? If you had the graph, this is not a real question you get on the exam because the answer is clearly just 0. I know this limit is 0. But if you didn't have this graph, right, how would we possibly come up with that? Because we're not going to factor this, right? This is not, you can't factor cosine of x minus 1. There's no real tricks we can apply here. And it turns out that this form, where the numerator is equal to 0 and the denominator is equal to 0, can be figured out through something called L'Hopital's rule. And so here is L'Hopital's rule. If you go to take the limit of a function, and this is poor notation here. This should really not say this. You never want to write 0 over 0. But if you get, when you try to plug in 0 over 0 or infinity over infinity, it turns out you can find this limit by taking the limit of separately the numerator's derivative divided by the denominator's derivative. So I'm going to hit a couple key points here and then show you some examples. Number one, this only works if when you first plug in, you get 0 over 0 or infinity over infinity. And if you get that, then you can do L'Hopital's rule. You can take the derivative of the numerator, take the derivative of the denominator, and try plugging in again. The really important caveat here, a lot of people try and take the derivative of the whole fraction using the quotient rule. There is no quotient rule here. This has nothing to do with the quotient rule. This is a separate thing called L'Hopital's rule. The numerator and the denominator you treat separately. And again, we'll see why on Wednesday. But coming back to our original example, right? We know this answer is 0. And so here's how I would do this on an AP exam. I would say the limit as x approaches 0, and I'd even number it, of the cosine of x minus 1 equals the cosine of 0 minus 1 equals 0. That equals 0, right? And maybe, when I first try this out, I actually do plug it in and I get that this is 0 over 0. The first thing I would do is cross that out because it's not actually a true statement. The second thing that's true is that the limit as x approaches 0 of x squared minus x is 0 squared minus 0 equals 0. And so if this was an FRQ, then I would say 3, therefore, L'Hopital's rule, and I'll just abbreviate it, LHOP, applies. L'Hopital's rule applies. And so what we can do is we can take the limit as x approaches 0 of the cosine of x minus 1 over x squared minus x, and I can say that this is equal to the limit as x approaches 0 of, let's take each of these derivatives. The derivative of the cosine of x we know is negative sine of x. The derivative of x squared minus x is 2x minus 1. And so let's try and plug this in again. We'd have negative sine of 0 over 2 times 0 minus 1. Well, the sine of 0, okay, what's that going to give us? The sine of 0 is 0. So we still get 0 on the top, but now we get negative 1 on the denominator. This is a perfectly fine thing. 0 divided by anything is 0. Don't forget, you can divide 0. You can divide 0 by 5, by 10, by 20. You just can't divide by 0. And so through L'Hopital's rule, we get that correct answer there. Okay? Let's do one more example. Really, I want you to focus on pretending this was an FRQ. If this is an FRQ, you would have 1 point for stating these separately. If you have 0 over 0 written on your paper like this and you don't have it crossed out, you lose that point. A second point for saying L'Hopital's rule applies, and a third point for actually working it all the way out to the end. So let's do one more of these, and then the rest of it will be yours for the Delta Math. So if we have the limit as x approaches 2 of this function here, and let's say I just jump straight into it, and I'm working out my FRQ, and I say, okay, this is 3 times 2 squared minus 7 times 2 plus 2, all over 2 minus 2. Alarm bells should already be going off. This would be 12 minus 14 plus 2 over 0. This is 0 over 0. Okay, so what I would do here is I would immediately cross all of this out, because now I know this has to be a L'Hopital's rule problem. And so I actually need to, in steps 1, 2, and 3, establish the conditions for L'Hopital's rule. I never write this. I never write the limit equals 0 over 0. Why not? Because it's not true. That's not what the limit is. The limit's going to be a real number, so you want to avoid ever writing something that isn't true. That's kind of the reason why. All right, rant over. So let's do one more of these. What I would say is, I would say the limit as x approaches 2 of 3x squared minus 7x plus 2. They know you can plug that in. You can just say that that's 0. That's fine. The limit as x approaches, especially if we've already done it and crossed it out, of x minus 2 equals 0. Therefore, L'Hopital's rule applies. Ding. 1 point right there. 1 or 2, depending on the year. Then I would say the limit as x approaches 2 of 3x squared minus 7x plus 2 all over x minus 2 is equal to the limit as x approaches 2. And they can tell you're taking a derivative. You don't need to actually say what you're doing here. You can say, okay, the derivative of 3x squared, so let's take the derivative with respect to x, is 6x minus 7. And that's going to be all over. The derivative of x minus 2 is 1. We plug in here. We'd have 6 times 2 minus 7 over 1. We'd have 12 minus 7 over 1. We would get 5 there as a final answer. And so maybe we can just kind of finish this off today by looking at the Desmos. And I've been having a lot of trouble with that. I don't know why. Doesn't want to do this anymore. Used to be, there we go. Oh, lost it again. All right, well, that's not going to cooperate, but trust me, you could look this thing up. Maybe if I go fast enough. Okay, I got it. Let's just check this one to make sure. So we'd have 3x squared minus 7x plus 2, all divided by x minus 2. And so I didn't really even try and factor this one. Maybe it could, I don't know. But let's see what happens here when x is 2. If I zoom in, there it is. It's undefined at 2, but the limit is clearly 5. Could I have factored this? I'm actually not sure. Let's see. 3x, x, let's see. Oh yeah, I could have factored this. So we could have had minus 2 minus 1. So you actually, this is interesting, you could have factored it. The x minus 2's would cancel, and you'd have 3x minus 1 over 1, and when you plug in 2, you'd get 5. So that is actually a really good one to close on here, because two things. Number one, if you're not so great at factoring or you just can't see it, L'Hopital's rule will work instead of factoring if it's a 0 over 0. But a lot of these you legitimately will not be able to factor, or as you're going to see in the Delta Math today, you might get it from a table or a graph or some way that cannot be factored.